Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's do the Python video of module number 3, ETS. So here's a GitHub and you go to deep forecasting, lectures and codes, and then module 3, exponential smoothing. So this is where we're going to talk about basically the methods and the models that we created in the last lecture video. So if you haven't watched the theory lecture, I highly encourage you to start from there, and then after that you can jump into this one. So there are two files here. One is for basically I call it module 3 moving averages. So this is for those of you who want to replicate. Let me actually go ahead and open it. Who wants to replicate the plots and charts that we had in the lecture video, in the theory lecture on the slides. So basically, if you can replicate those ones, I will leave it up to you. You can basically go ahead and read this notebook. It's pretty straightforward, and I'm pretty sure that you can take care of it. And there is another one, which is module 3, exponential smoothing, the ETS, the Python notebook. So this is the one that I want to talk about it today, and then walk you through all the code and everything. All right, so as always, you can either run this in your Google Colab. If you do that, make sure you make a copy to your own drive, and then that's your version. Or also feel free to run it here. But if you run it here, just be aware you cannot make changes, right? So let me actually show you the timeline. Basically, what we're going to do is cover everything we discussed in the theory lecture when it comes to exponential smoothing methods versus ETS models. We're going to do both of them using Pycaret Python package. So Pycaret is actually it's very useful for time series. It's a wrapper around multiple Python packages, including skTime. So this is one of the better packages when it comes to doing time series analysis. Again, there are many good models. We talked about it in the environment lecture video, that setting up your Python environment. What are the time series packages? You know, if you want to check those packages, make sure you watch that video again. All right, so when it comes to installation for this class, you can go ahead and install the light version. Just do pip install Pycaret, or if you have already installed the full version on a local computer, you can go ahead and change the environment and then use that environment. But for those of you who wants to follow and code in Google Colab, just uncomment this part and then go ahead and run it. So it's going to take a couple of minutes. And if you want to do the full version, obviously you can go ahead and do something like this. This is going to be the full version. Okay. All right. And yeah, this is basically what we're going to go over. We started working with a very simple data set. As always, you know, we start with the airline passenger data set, and we're going to look at some examples for stock price. So again, looking at the most well-behaved time series versus the most challenging. And then any other time series is going to be something in between. And then we talk about the methods, starting from SES, then go to Holt linear trend, talk about Holt winter methods, then we move on to models. We predict model, finalize model, and then I'll show you how to save model, and then if you need it later on, how we can load that model. All right, so for today, I would rather to do it on my local computer because I already have Pycaret installed on my local computer, and I prefer to work with VS Code. So here I have the VS Code opened. Let me go all the way back to the beginning of this notebook. And this is the folder. Basically, this is a GitHub folder, and this is module 3, and I'm looking into this module 3 exponential smoothing _ ETS. All right. So the first thing you need to do is make sure that you're picking up the right kernel. You can do Control-Shift-P or Command-Shift-P, or simply select kernel from here. And I already have Pycaret, as you can see. Actually, I have two. I can do either deep forecasting or Pycaret. Either of them has Pycaret installed on it. So I'm going to go ahead and do deep forecasting. So this is the environment that I created for the course. And I added a bunch of packages to that, including Pycaret, Yahoo Finance, and etc. Okay. So for econometrics part of the course and the machine learning section of the course, we're going to stick to this deep forecasting environment. And later on in the deep learning section of the course, we will go back to our Keras environment. Okay. So now it should be all good. And installation, again, we don't need to do that. And we can quickly check what is it. Pycaret version as of today, it's 3.3.2. By the time you are watching this video, there might be, I don't know, version 4 probably is going to be out. And then If that's the case, just make sure, in order to make sure that this notebook is reproducible, you have to just be aware that the version that is up and running right now is 3.3. If you have anything above 3, this is going to be consistently and smoothly running. Okay, so let's go ahead and import the packages. I can go ahead and minimize the left-hand side. All right, so this is importing packages. And actually, let me go ahead and increase the size as well, because I just want to make sure that this font size is big enough. Okay, I go to my setting, and then there's this font size. You can change it from 16 to 20. I don't know, maybe 20 is too big, but yeah, I think it's going to be easier for you guys to read it if you're watching a video on an iPad or iPhone. So it's going to be easier if you watch it on a smaller screen. Okay, so let's continue. I'm going to go ahead and import the dataset. So Pycaret, it has a module called datasets, and from that you can use this get data, and then off of get data you can get access to a bunch of time series, including airline passengers data. This is a very classical time series dataset. And however, you can also import the airline passenger dataset from my GitHub repository. It's called airline passengers, and the index column, we want to make sure that we have the right index as a time, which is month. So either way, it should work. So I would rather to call it month and then work with that data set. All right. If you're working with pandas, your first job should be changing the type of the index to date time and then to period. So this is very important. Actually, I want you to take this step very seriously, because most of the errors that you might get down the road is incompatibility of the Python package with your time index, right? So you should understand, when you're working with time series, each package is requiring what kind of time index. Pycaret wants pandas daytime index, and on top of that, it wants you to specify the periodicity. Is it monthly data, daily data? What is it, right? So I'm going to show you the index. So this is the index. As of now, as you can see, now importing from raw CSV, the index type is an object. So Pycaret is going to complain if you pass this data to it. So you have to make sure that we change it to date time. So how do we change it? We can use from pandas package to date time and change this index. Right now, we are not overriding the index of the data set. I just wanted to show you how it does it. So now it's date time. And now I'm going to write another cell and override the index of the data frame to date time, and also specify the periodicity, which is monthly, right? So you have to do that. Otherwise, Pycaret is going to, the package that we're going to use is going to complain. All right. So now we have the right data type. We have the right period, which is month, and we're good. We're good to go. So we can quickly visualize and remind ourselves what does the airline passenger data look like. And as you can see, there's a clear upward trend, there's clear seasonality, and we know that the magnitude of seasonality is increasing. So this is a sign that basically we most probably are going to end up need a model that has trend and seasonality in a multiplicative fashion, right? So this is the skill that I want you to develop out of this course. Before running any model, by simply looking at the data set and the behavior of time series, you should have some prior belief that which model is going to perform better, right? So for example, a fair benchmark for this data set obviously is not a simple average. It's not the grand mean. It's going to be, at the very least, it's going to be your naive forecaster, right? So we talked about all these things in the theory lecture as well. Make sure that if it doesn't make sense, please make sure you watch the theory lectures carefully and then come back. All right, I'm going to import everything from Pycaret time series. So, and now off of that, we can create an experiment, right? Let me actually go back and open the documentation. There are a couple of links I want to open. So one is for Pycaret, the other one is for skate time. So down the road, when we need to see what goes inside each model, we have to go to the parent Python package, which is skate time for time series. And this is documentation for Pycaret. So this is where we are. We're looking into time series functions and modules. And yeah, we can set up an environment, we can create model, we can compare those models, tune a model, blend, and you can mix the model in an ensemble way, or we can stack them, we can blend them together. And obviously we're going to use this plot model function a lot. You can predict, you can finalize the model and deploy the model if you wish, right? So these are the functions that we're going to mostly work with throughout the semester, as we are talking about the machine learning and the econometrics section of the course. And I think one of the most important functionalities is this setup, right? If you click on any of them, it's going to give you an example and obviously what you can pass to this method in Python, right? So there are tons of things you can play around with, but the most important one is obviously what is the data and what is your target variable. If it is multivariate, you have to specify, what is your target variable, right? And then you have to provide some observations into the features as well for the features. But here, this is this is the airline passenger dataset. It's univariate, and our target variable is going to be passengers, right? And yeah, there are lots of things you can play with. You can ignore a bunch of features, again, if it is multivariate. And you can do imputations. You can imputate your target variable using drift or linear or nearest observations. So these are the methods you can use. For example, if it is a stock price, you can do backfill, you can do forward fill. So these are all different things you can use for imputing your target variables. So here, this is our airline passengers. There's no missing variable. We don't want to impute things, right? So we're not going to use this functionality. You get the idea. There are tons of things. I want you to just take your time, pause the video, look at these functionality when it comes to setting up the experiments, right? So let's go back to the VS Code. Let's just scroll down. We were here, right? So let's set up our experiment. I'm going to say this is a time series forecasting experiment. Let's create a placeholder for that. It's an object, exp. You can call it experiment 1, experiment 2. So you can create multiple experiments in one notebook, and you can run models on different experiments with different setups, right? For example, in one experiment, you're removing outliers. You are normalizing the data. In the other experiment, you're not doing any of them, right? And you want to compare them. You want to run a horse race between, 20 time series models for different experiments. So this is very useful, very handy functionality that Pycaret provide. So for us, let's keep it simple. This is just day one. And as we progress, we're going to make it more complicated. So off of this experiment, I'm setting up this experiment, passing the data frame, my target variable. This is my forecasting horizon. So forecasting horizon says that whatever data you have, the last 12 observation is going to be your test set, right? Of course, we can forecast into the future as well. Later on, when I'm plotting things, I can show you how we can forecast 36 months in advance and things like that. But this FH here simply means that out of 144 observations that you have, remember, this is for 144 observations, how many of them is train, how many of them is test, okay? And coverage, 90%. So this is if you're using the ETS model, right? So from lecture theory, hopefully you remember that the exponential smoothing methods, they give you point estimate, right? They don't give you confidence intervals or prediction intervals. And however, the ETS models, because we introduced that noise, now we were able to back out the variance of the data using, let's say, maximum likelihood estimation. We could estimate those formulas for variances. And then with that, we could create some confidence intervals, right? If you're using a model like ETS model, that coverage is going to be 90%. Okay, you can change that. Again, this is one experiment. So you can do experiment 2, 3, and change all these things. And quickly going down the output of this cell, let's see. Yeah, if you run it for the first time, it's going to take a couple of seconds. But again, depending on your computer speed or Google Colab resources that are provided to you, this may take longer or shorter. Okay. What do we have? So for example, we have this, it shows you how many missing values you have, what is your train, what is your test, and if you're doing cross-validation, what kind of cross-validation are we using? So this fault generator is expanding window splitter. Remember that we talked about it when you're doing cross-validation. We're going to re-emphasize these concepts in the machine learning section of the course as well. Time series cross-validation is tricky. You cannot simply shuffle the data. So that's why we have to do time series cross-validation. So one method of time series cross-validation is expanding window splitter. We are using 3 folds. Don't worry about these things for now. When it comes to when we get to the machine learning section, I will talk about them a lot in more details. Then let's see, what else do we have? So for example, seasonality, is a seasonality there or not? The answer is yes. What was the seasonality periodicity? It was 12. This is month. And you can, again, you can read through all these things and then use ChatGPT or Claude to help you understand what each line means and to educate yourself, right? But I don't want to make this video too long, so that's why we should skip some of them. And yeah, then off of that experiment that you created, obviously you can call some methods or functions, right? So the first one we can do is check status. So this is going to run a bunch of statistical tests for normality, for if it is white noise or not, for stationarity. For example, we are doing ADF test, look at the p-value. P-value is crazy large. So we failed to reject that the data set is non-stationary. So yeah, so this is, yeah, we failed to reject that the data set is non-stationary, right? So it means that it's going to be non-stationary. And obviously this is a non-stationary data set, right? So the same story for other methods like KPSS and et cetera, right? And so this is basically, there's nothing new here. In the theoretical lectures, we already talked about the stationarity. Later on, we're going to formally introduce these two tests and see. But in a nutshell, simply if your p-value is very large, so here you fail to reject non-stationarity. For KPSS, that's the other way around, because the null assumption is different. You want to get a small p-value for this one. For this one, you want to get a large p-value. If you get that one, it means that your data set is non-stationary. All right, so then the next function we're going to look into is plot model. So if off of that experiment, if I do plot model, I can do, let me actually open the documentation for you one more time. So let's go to the plot model. And as you can see, these are the things that you can put, right? You can say TS time series plot. You can do train test split. This is what I'm using. It's going to show you the train test split plot, right? Like this, train test split. This is my train set, this is my test set, and etc. Right? What else can we do when we use plot model? We can plot ACF, right? So I can do ACF. And if you want to change the lags, you have to do data quarks, and then number of flags, pass a dictionary, number of flags is 36. So obviously if I change it to 24, it's gonna do 24, right? So this is not a video of me going through interpretation of things, so hopefully you understand how to interpret these things. This is scallop thing, shows that the data set is seasonal. This downward sloping means that the data has trend in it, and etc. What I want you to be aware is that, okay, how did you know that if you want to change the number of flags, you have to do data quark? So this is a question that I typically get from students, and even if you read the documentation, it's not there. So you cannot find it in Pycaret documentation. What are those data quarks and etc., right? So some of them are there. So for example, let's see. For example, the order list is here, the lag list is here for ACF, PACF plot. But some of them, so let me see, the number of flags that we use is not here, right? Yeah. And a bunch of other ones down the road, you will see that you cannot find them in the documentation. So how can you find it if you're using Pycaret package, right? So this is an interesting question. So if you scroll down, there's a link here. Basically, it sends you to the GitHub folder for Pycaret, right? We're going to look into the forecasting container for this extra functionality. You can click on this. Basically, this is your Pycaret time series forecasting and functional. And now here, this is a source code, right? The source code of Pycaret. And this is where you can find all those tweaks and tricks when it comes to using Pycaret, right? If I do quarks, data quarks, actually we can do data quarks, right? Data underscore quark. Let's see. Yeah, these are all the ones that you can use, right? I think I can do number of in lags, yeah. So depending on what function you're using, you can look for this term data quarks and see what are the switches available, right? We can do n lag. So this is where I got that one. So we're using, when you are using ACF, PACF, or CCF, so this is a thing. You can do n lag and change the number of lags, right? Seasonal period type, is it additive, is it multiplicative? Again, depending on what plot you're using, these data quarks make sense or make not, right? But here's where you can find it. So this is what I want you to be aware how to do that, because surprisingly, well, maybe not surprisingly, Even as of today, the better models out there like in Sonnet 3.5 from Claude or GPT-4o from OpenAI, they are not good at helping you with these little things in coding when it comes to Pycaret, right? So you have to find it. You can give it a try and see that neither of them is going to show you that the right way to change the lag was this, right? You can give, again, but now you know where to find it from the source code and how we can manipulate those things, right? So this is the ACF plot. We can do the PACF, and then still this seasonality is large here, and it seems that one lag is enough. Nothing else matters except there's this seasonality things, right? Again, interpretation of ACF, PACF plot, we talk about it in the lecture video as well. Then we can do decomposition, right? So I'm using the decomp from Pycaret. Plot functionality is going to give me this classical decomposition. By default, it's additive. I can change that default to multiplicative if I simply change the data quarks, for the type to be multiplicative. And we should be able to read these charts very easily, right? This is the blue one is my main airline passengers. Now we have seasonality. Then we can extract the trend. Whatever is left over is going to be your residual, right? And obviously this residual is going to go around 0 because it's an additive model. If I change it to multiplicative, that residual is going to go around number 1, right? So again, in the theory lecture, we talk about all these things. But these are simple decomposition of your time series. This is our first Python video for econometric section, ETS models. Basically, these are decomposition-based models. We want to say, let's create a Holtz linear model, right? To that, I care about this trend component. Let's do Holtz Holtz winter model. So I care about seasonality and trend. You get the idea. All right. Then, what are the available models in Pycaret for time series? These are available models. This is your naive forecaster. This is your grand mean, simple average. This is seasonal naive, polynomial trend, ARIMA, auto ARIMA, exponential smoothing. So this is the one that we're going to cover, these two, exponential smoothing and ETS. And look at that. If you see where it's referencing, this one is reading information from SkTime, right? So that means if you want to change the functionalities of any of these models, you have to go to the documentation of SkTime, not Pycaret. And that's why I had it open as well, right? So this is SkTime. You can, for example, do ETS and then find the ETS model. This is the auto ETS, SAS forecast. These are the auto ETS. You get the idea. I can go to the models on the left, right? And yeah, you will find all the documentation of the models. For example, ARIMA, ETS, VAR, you name it. All these documentations are here, right? And Pycaret, if you want to change those, for example, models, this is where you can find the information, right? So open the documentation of SkTime, and this is where you can find what you need, how we can add the trends in an additive versus multiplicative. Do you want to have trend? Do you want to have damp trend, or et cetera, right? So if you see me in these notebook that I'm playing around with those things, that's where it's coming from. So just be aware. Yeah, there are tons of other models as you can see. I think these ones are all classical econometric models. These are your benchmarks, and these are all your machine learning models, right? So we can, in the theory lecture, we barely talked about BATs and T-BATs, right? So this is where basically the seasonality is not classical regular, like it's not weekly or monthly, right? So we have strange seasonalities. Then you can use trigonometrics models, including sine and cosine, to capture those seasonalities, basically including Fourier seasons and things like that, right? And yeah, this is a mix of, for example, autoregressive components, trend, seasonality, and this trigonometric seasonality, right? So we don't have a specific theory lecture for BATs and T-BATs, but just be aware with what you know from the theory lecture, you can understand the basics of this, right? So then you can use ChatGPT to help you understand the model better. But at the end of the day, these models are a combination of what you already know from the course. And the rest, this is basically the machine learning versions, right? So for example, we have linear model, we have, this is elastic net, ridge, lasso, and what else? We have KNN, random forest, light GBM, cat boost, and etc. Right? XGBoost must be there as well. Yeah. So probably this is a light version. If you do the full version, you will get access to all the models, right? And there is one thing before we move forward. Again, this video is going to become a little lengthier because we are setting the scene, right? I'm introducing you to the Pycaret and everything time series. So next time I'm not going to repeat myself over these ones, right? So just bear with me. And here, for example, this CDS stands for conditional, deseasonalized, and detrending. This is really, really important because remember, guys, from module 1, where we were talking about econometrics versus machine learning high level, we need to transform the data, prepare it for supervised machine learning. This is where it's gonna, we're gonna address that, right? So we're gonna make sure that the models, the machine learning models, are going to work with stationary version of the data set. There, if you shuffle the data, you're not doing it completely wrong, right? So again, don't worry about the details, but I want you to know that under the hood, Pycaret is taking care of all those time series tricks and challenges when it comes to applying machine learning models to time series. So when you see this CDS, so this dataset is already deseasonalized and detrended, so it's most probably stationary. And now let's do analysis on that. And then when you want to predict the outcomes, it's going to transform this back to the original dataset, right? You don't need to be worried about, okay, I need to detrend it, deseasonalize it for prediction. I need to add back the trend, add back the seasonality. You don't do any of these things manually. So Pycaret is going to take care of that. Yeah. So now let's get into so that was the basic setup of Pycaret. Let's get into the exponential smoothing methods. Okay, so here are relevant documentation. So this is skate time, exponential smoothing. So again, where we see how we can play around with the features, that's where it's coming from. Trend, damp trend, seasonal component, seasonal period, initial value. So this is for optimization, don't worry about that. So these are for optimization when we want to find the parameters of the models, right? And yeah, we have a smoothing trend. Yeah, you get the idea. Just read the documentation. Hopefully it's straightforward and it helps you to get what you need, right? And there was another link, which is Pycaret model container. Again, guys, when you're working with the Python package, even if it is well documented, sometimes you cannot find everything you need. So you have to look into the source code, right? So that's where you can find some functionalities of those things that so let me actually do exponential smoothing, right? So exponential smoothing, this is a class, right? And it's telling you where it's coming from. It's coming from skate time, right? Exponential smoothing skate time. So if you want to read the documentation, so that's the name that you should use in Google, for example. Say exponential smoothing skate time, right? So that's where I found this link for you. So if you're curious how we can get those things, right? And yeah, I assume you have watched the theory lecture and you're just ready to implement what you learned, right? Let me actually open the PDF to show you something. Yeah, let's go to oops, not this one. Let's go to the PDF of the course, so of this module. So yeah, the slides, and I want to bring up one slide very quickly. That's basically, yeah, here. So this is what we're going to do, right? So we're going to create the SES. This is good when there is no data, when there's no trend, no seasonality. Then we're going to extend it to holds linear, adding a simple trend, then damp that trend, then use add seasonality, holds winter, and finally we can work with damp trend seasonality, right? And yeah, this is what we're doing. So now let's go back. So starting with SES, simple exponential smoothing. Off of that experiment, let's create a model. The name of the model is exponential smoothing. Trend, no. Seasonality, no. There's no seasonality period as well, because you want to say that there's no seasonality. Cross-validation, for now, we're going to set it to false. Later on, as we cover the machine learning section of the course, we can switch it back to true. Then the performance metrics that's going to report, it's going to be basically cross-validated metrics, not necessarily from the test set, okay? All right, then if I run this line, it's going to show you what is simple exponential smoothing numbers are, right? And the performance metrics are. So this is your mean absolute error, 76. The unit is the same as the target variable, which is airline passengers. I think it was millions. And then this is root mean squared error, mean absolute percentage error, 14%. This is way off. No. Symmetric mean absolute percentage error. Again, this is a large number. And your R-square in the test set. Guys, what is the test set? Because I set up the experiment forecasting horizon to be 12, so test set is that 12 observation. And we get a negative R-square. This makes perfect sense. This is what I want you to learn, right? So if I go back, remember, this is my original data set, right? What is seasonal exponential smoothing? It's going to be a simple line between your simple average and your naive forecaster, right? Oh, let's say that it's a line, it's a horizontal line somewhere. That horizontal line obviously is not gonna have a good R-square. So when you get an R-square of negative, it means that it's even worse than the average. So for time series, just be aware, we don't necessarily look into R-squares. That's not the right metrics for many applications. And I think at some point, yeah, down this notebook, I'll explain what are each of these things are and then how you should read them. So I think many of you guys are already familiar with the basics outputs, these 5 metrics. These might be new to you, what is MAZE and RMSSE. So this is mean absolute scaled error, and this is root mean squared scaled error. And scaled, it simply means that let's compare the performance of your model relative to naive forecaster. So relative to your naive forecaster, your model is 2.5 times worse. So if this number is less than 1, it means that your model is outperforming the naive forecaster. If it is greater than 1, it means that it's simply worse than that. So in either case, and interpretation of MAZE and RMSE is relatively the same, right? So in terms of RMSE, this one, now this model, this SES is 2.98 times worse than a simple naive forecaster, right? Again, it's not surprising at all. In the theory lecture, we talked about it too, right? This is the data with trend and seasonality, and you're using a model that doesn't capture trend or seasonality. So nothing special here. Off of that model, you can get access to the parameters if you do get params. And basically, again, nothing there, right? There's no trend, no seasonality, no damp trend, and etc., etc. And obviously, you can look at the performance of this model in sample, right? So if I do plot in sample, it's going to show the performance in sample, right? So the blue line is original observations, and the orange ones are what your model has. And in order to give it a proper name, I use data quarks labels, and I pass a list of how many models we have. Here we only have 1, and so that's why we are using SES. Okay, so this is in sample predictions. You can get access to these in sample predictions as well, right? So for example, I want to create some in sample performance metrics, because guys, by default, Pycaret is going to give you the out of sample or test set performance. And you might wonder, okay, what is the in sample performance of one? Because by default, it doesn't give it to you. You have to figure it out, right? So let's do it together. So you can visualize it, but it doesn't tell you what was R-square, what was RMSE, what was MSE, or things like that, right? So let's see how we can create those metrics for ourselves if you're curious about the in-sample performance metrics as well. So here I'm showing you the index only of the train set, right? We are excluding the last 12 observations. So this is the index of train set going from January 1949 to December 59, okay? All right, then we can plot the residuals. Let me actually show you. If I use this function, predict residuals, this predict residual is going to give me the residual for the train set, right? So this is the residual in the train set, 132 observations from 1949 to December 59, right? And right there, I want you to go back to the theory lectures and think about it. Is this a good residual? Obviously not. What is a good residual? A good residual should look the same as white noise. This means that if your residual looks like white noise, your model has captured everything it requires to, right? But this one, obviously I see seasonality here, I see heteroscedasticity, I see increase in the magnitude of residual. There's so many things wrong with this residual of the, again, in sample performance, right? So this is a strong signal that you don't have a good model. This model that you call SAS, even in sample, it's not performing well. Guys, don't be fooled or misguided by saying, okay, you say, okay, this orange one is okay, but no, this one relatively one shift, one lag, this is killing the performance metrics, even in the train set, right? So, and the residual is screaming at you that this is not a good model, okay? All right. So again, the function you could use is predict residual to give you the train set residuals, and then you can use that one to figure out what are the predicted values as well, right? So the predicted values, y minus y hat is your residual. So if you have y, if you have residual, you can back out the y hat. So that's one way to do that, right? The other way is just simply use the predict function, right? So we already answered this question, right? What's wrong with these residuals? So what are the predictions? Remember, in sample predictions, I need to create 132 of them from here to here. And for example, the first one is 118.46, right? So let's get to that one. If I use the predict function off of that model and then just use the train set, it's going to give me those predictions, right? So this is how we can get access to in-sample prediction in Pycaret, 118.46. And alternatively, you could do y minus the residuals to get the y hat. All right. So performance metrics, I think I barely talked about them, but here's a list for you. Make sure you go through them. These are classical time series performance metrics. Make sure you understand them, especially the pros and cons, because yeah, for example, MAPE sounds interesting. It's very interpretable, mean absolute percentage error, but it comes with a big caveat. If your numbers are small, this MAPE can be exaggerated. For example, look at that. If I go from number 100 to 101, what is the error? 1%. If I go from number 1 to 2, the same unit, right? What is the error? 50%. So you have to really look into that. Is your what is the level of your target variable that you're predicting? Are there small numbers, big numbers? So be very careful when you're interpreting MAPE. So here are the formulas. Again, these are pretty straightforward. Mean absolute error. So you have the error to look at the absolute value. This is percentage-wise, this is root mean squared error, and this is R squared. So for time series, we really are not necessarily interested in R squared because R squared shows the proportion of the variance explained by the model. And this is most of the time not interesting to us, right? What you care in time series prediction is that how off your predictions are from the realities, right? So you need the units related to that. That's why we look into errors, right? This letter E. Then we look at different version of that. Root mean squared error, mean squared error, or mean absolute error, mean absolute percentage error, and you name it, right? So if you want to see what is the full list of all these matrix using SK-time, there's I don't know, 50 of them. So look at that. These are all different metrics. Depending on the context and the problem set that you're dealing with, one of them might be a better fit compared to the other one, right? But just be aware there are dozens of them, right? So these are all different metrics you can use. Mean absolute scale error, median absolute scale error, all the way, look at that. There are lots of them, right? All the way to prediction ratios and et cetera, et cetera. Okay, let's go back. Okay, now, I here created a function, I call it time series metrics, and this function is just taking two values, y and y hat, your actuals and predictions. This is, again, you can use ChatGPT, say, hey, I want to create a function to summarize these 5 metrics for me. Okay, so this is basically what I did. And then it created this nice function. I'm going to use those metrics from scikit-learn package. So from scikit-learn, I'm importing mean absolute error, R squared, mean absolute percentage error, and mean squared error. And yeah, these are the ones that I'm going to put in my time series metrics. And basically, again, this is directly coming from the scikit-learn, etc. Okay? And down the road, you can calculate some of them that are not here, right? Yeah. So, and we put it in a nice dictionary. We add some prints to the end of it, and then this is going to be our function, right? So now remember guys, I have, let me actually show you. I have the actuals, we call it Y. I have the predictions, I call it Y predict. And now I have everything to pass to this function, and nicely this function creates the performance metrics for me in the in-sample, right? So these are the in-sample performance. So this is something that Pycaret by default doesn't give it to you, right? So what Pycaret gave to you was the performance in the test set. So these numbers. If you're curious how to do it in sample, so these are the performance in sample. Once you create this function, the rest is easy peasy. Later on, you can simply call this time series metrics and then pass actuals and predictions, and then that's it, right? It's going to give you this nice output. So in the in sample in train set, if you wish to call it, the mean absolute error is 23, mean absolute percentage error is 8.9, root mean squared error is 31, and your R square is now positive. It's not negative. Again, because in sample it's working better, but please be careful. This is very misleading. You might say that I have a time series model with 91% R square. Isn't it great? The answer is no, absolutely not. Because in time series, I cannot care less about R squares. This is an awful model. I don't like to see something like this in the train set. Okay. Hopefully you get the idea. How do I know that this is awful? Because look at the MAPE, 9%. This is crazy large. Okay. All right. Let's keep rolling. The next one, we can plot the forecast. And for forecasts, we can change the forecasting horizon, right? So by default, the forecasting horizon is going to be 12. And this is SES. As I explained you earlier, it's going to be a flat line. Obviously, it's not a good forecast. That's why the performance in the test set was so bad. I can this is using 12 month. I can forecast into the future by changing this data quark FH to 36. So this is how it's going to look like. So 36 into the future. And then obviously I can look at the values of those forecasts. So if you want, you can use the predict function. Now I'm using the last 12 observations, right? So this is your forecasted values. So 1960, January and onwards, this is your 1960, which is 404.78. So this is your 404.78. All right, so yeah, what else? Let's see. So again, this is basically, if you do ses.predict, by default, it's going to give you the forecasted values, right? Even if you don't pass the last 12 observations. Okay. All right. So now look at that. I want to look at time series metrics in the test set, right? So if I can use my time series functions that I created, and I'm passing the test set with, these are the predictions, right? So these are the actual values in the test set, 12 observations. These are the prediction in the test set, 12 observations, right? I can run it, and this should be pretty much the same as what Pycaret by default output for you, right? So remember, when I did SES, what was it? When I was creating this SES model, by default, it gave me those outputs, right? So here, sorry to give you a headache. I don't want to go back and forth, but there you go. Okay. Alrighty. So let's scroll down. Where were we? Yeah, these numbers should be familiar to you, right? And you can use some built-in functions as well, right? So for example, I say exponential, this is experiment, predict model. What is the model name? What is your forecast horizon? These numbers should match. The one that you manually put together versus these ones. The R score is -91. Your root mean squared error is 103, and etc. Okay. Your MAPE is 1427. So we should see that 1427 somewhere. There you go. Okay. So yeah. And I think we already talked about it, but this is just for your reference. What is Maze and RMSSE, which Pycaret by default give you? Mean absolute scaled error, root mean squared scaled error. So this is a scaled relative to your naive forecaster. These are very bad number. So your model in the test set is 2.5 times worse than a simple naive forecaster in terms of mean absolute error. In terms of RMSE, it's 2.98 times worse. Okay. So we knew that. This is not a strange. We already expected that because SES is suited for a model with no trend and no seasonality. Remember this one. Yeah. Let's see, where about this, there you go. Now we're gonna move on to Holt's linear trend, and then damped trend, and Holt winter, and Holt winter damped. So I'm gonna speed up from here because you know the basics, and let's just roll, right? So I call the Holt linear trend, I call it HT. Create model, the same method, but now the trend is additive, seasonal, no cross validation. Okay. This is already better, but not that much better yet, right? So you can look at the plot, you can look at the forecast 24 months into the future, you can change the label, Holt linear trend. I can scroll down, look at the predictions. I can look at the predictions for the 24 month, right? So starting from January 60 all the way to December 61. You can go, I don't know, whatever, 120 periods, 10 years, right? And you can create those things. The next method is Holt's winter method. Again, the same model, same methodology, trend additive, seasonality additive. What is the periodicity of seasonality? 12, cross validation false. So this is getting a lot better. As soon as we add seasonality and additive trend, it's a lot better. Look at MAPE, it's 2.8% only. Here, your MAPE was still 12.5%. And then previously it was crazy large, right? 14.28. Now we're getting there, right? And the next model we pulled together is Holt's winter multiplicative. This is if you think that the magnitude of your seasonality is increasing over time, so you should add it in a multiplicative way versus linear way. So let's go ahead and do that. Okay, so your MAPE is also decreasing, so it's 2.2. It's a lot better now. And this is, again, guys, don't pay too much attention in the R-square in the test set when it comes to time series forecasting. That's not a variable of interest for many applications. Sometimes we care, but not in examples like this. Because you saw that SES in the test set was negative, and then even in the train set was large, but it was not a good model. Okay. So then we're going to damp this thing. We're going to say exponential smoothing, damp trend, yes, and seasonality and multiplicative, and etc. Again, how do I know these things? You have to go back to the documentation for exponential smoothing and then read the documentation. Okay. If you do it enough time, you will become super familiar with that, and it's not going to be stressful at all figuring out all these functionalities. Okay. All right, so then let's say you like this Holt's winter multiplicative model because it has the smallest MAPE, or it has the smallest MAE, mean absolute error, and it's on 2.21%. And you want to look at what were the parameters inside that model. So this is what you can do. You can get the parameters, and then if that's your winning model, you can plot it, or you can plot multiple models together, right? A cool thing about Pycaret is that when it comes to visualization, it's pretty straightforward. I'm going to go ahead and add, for example, 3 models here. Let's call them method for now, because you want to call these things exponential smoothing method versus ETS models, which I'm going to talk about them down the road. These are point estimates. These are not going to give you confidence intervals, because by construction, they're not able to do that. We can look at the in sample of these things. We can look at the labels, right? SES, Holt winter additive, Holt winter multiplicative. This is in sample, right? And now we can look at the forecast. By default, it's going to give you the forecast in the test set, which is 12 observations. So this is, again, in theory lecture, we looked into all these things, and it should be good to go. And then we can forecast into the future, 36 months. This is how it's going to look like. And as we talked about it, the SES is going to be the worst performance, because again, that doesn't make any sense to apply to a data set like this. Okay, but it seems that our Holt winter multiplicative one, it's nailing it, right? Because here, this is the first 12 observation in the test set that we have the actual values. Look at the blue one versus purple one. It's nailing it, right? So it's doing a very good job. All right. If you want to see which one is the best model so far, so I use this compare model method, and then I pass whatever model I have. I pass SES, Holt's linear, Holt's winter additive, multiplicative with damp. Cross-validation, again, for now, we're going to set it to false. But the right way of doing is just look at the performance of the model in the cross-validated version of the metrics, right? When we talk about the machine learning section, we're going to add that functionality as well. Here you can give it a try. You can set it to true and see what is the... Well, actually, let's go ahead and do that. Off of this experiment, we're comparing a bunch of models. Which one is the winner? So look at that. They're all the same. Methodology is exponential smoothing. How do I know which is which? So this is model number 3. So it's 0. Remember, Python indexing starts from 0. 0, 1, 2, 3. So Holt's winter multiplicative is going to be your model number 3. So that's the winner. The next one is HW damp. The next one is 2, which is Holt's linear additive. The next one is 1, which is Holt's linear. And the worst one is 0, which is SES. For this one, Holt's winter multiplicative was the best performance for all the metrics. Okay. And if I change it to true, it's going to do this. It's going to run the same models, but use the cross-validation metrics instead of the test set metrics. Okay, so this is going to take longer. And remember, again, we're going to talk about the details later on, but this is probably the correct way of comparing the structure of the models with each other. You have to look at the cross-validation metrics, especially if your data set is small, like what we have here. The same story. Now, as you can see, the same story is true. Model number 3, which is this one, is the correct one. Is the winner one, not the correct one. Okay, then you can see what was inside that model, right? So multiplicative, 12 period, monthly seasonality, and then trend additive. Okay, so according to the table above, our HW mult is the best performers. We can look at the residual of this model, right? So I can plot the residual of this winning model and do diagnostics. So this is a diagnostics. And does this residual look like a white noise? Not necessarily, but it's a lot better compared to what we saw for the residual of the SES, remember? So this means that we probably can improve this model a little bit, but not that much, because this residual, to me, obviously it's stationary, the variance is bounded, the mean is around 0, and then I don't see any autocorrelations, no clear autocorrelations going on here. So probably it's not a bad residual. And of course, we can test it against the white noise and see if it is, we can reject that null hypothesis or not, right? Histogram wise, again, ideally it should be normally distributed. Then you can look at the ACF and PACF of the residuals. There should be nothing there, okay? If you control, again, this is lag 0. We don't care about this one. Even lag 1 should not be significant. This one, it seems that it's a little bit of significant, but again, after that, there should be nothing there, right? Because if it is white noise. And PACF, the same story, QQ plot for normality, periodogram, if there's any periodicity left in the residual. So this is not bad. Again, you wish that it's not going to be like this. So maybe the seasonality is not perfectly captured, but you look at the performance of the model, it was not that bad, right? So yeah, we're done with methods, exponential smoothing method. Now let's go ahead and create some models on top of those methods. And from the lecture theory, I want you to remember that we said that exponential smoothing methods, they're going to give you exact same point estimates compared to ETS models. So when we go from method to model, it's not about point estimate. The point estimates are going to be exactly the same, and you're going to see that because the methodology is the same. The only difference is that ETS is going to create that confidence interval for you, but exponential smoothing methods cannot. By construction, they cannot. All right, now let's look into that part. Okay, now let's do the ETS models. So let me quickly remind you what are the available models in Pycaret time series. So in that environment or experiments, we already covered exponential smoothing methods, and now let's talk about ETS models. And this is basically where the model is, it's reading it from skate time, forecasting, ETS, auto ETS. So that's the name of the model, auto ETS. So if you go to skate time documentation, search for auto ETS or ETS, you will see that. So this is where Pycaret is reading information. As you can see, there's error component, there's trends, there's if you can damp the trend or not, there's seasonal component, and etc. Pretty much the same as the smoothing equation methods. The only difference is that now we have this error components, right? We can add it in an additive way or multiplicative way. So again, make sure you watch the theory lecture and this should make sense. So here we're simply implementing them. All right, so our first model, I'm going to do ETS A and N. The first one stands for additive trend. The second one, no seasonality, no trend, no seasonality, right? So additive error, no trend, no seasonality. So the name is ETS, additive error, no trend, no seasonality. This is equivalent to our point estimates for SES. So I say point estimate because we know that the SES cannot give us confidence interval. This one, however, the ETS can give us confidence intervals simply because we are adding this error component. We make some assumptions for that. Based on those assumptions, we were able to calculate the variance. We had a formula for variance, and then we come up with the formula for variance of predictions. That's why we ended up creating a confidence interval using these models. So I'm going to go ahead and run these cells. So the first one is ETS A and N. And these numbers should look familiar. This is pretty much the same as our SES model, right? Because again, the point estimate is the same. And if you want to calculate, for example, mean absolute error, you do y minus y hat. If y and y hats are the same between SES and A and N ETS, basically you get the same metrics. Let's go ahead and train our second model, ETS AAN, additive error, additive trend, and no seasonality. This is equivalent to our Holtz-Linter trend, remember? So again, these numbers should look familiar. The next one is AAM. So additive error, additive trend, multiplicative seasonality. Again, the notation is pretty straightforward. So we can train this one. And finally, we can compare the three of them, right? We know that this should be the winner. No, the additive trend and multiplicative. This is our Holtz-Winter equivalent ETS model, right? So let's compare them. Cross-validation for now, we set it to false. Later on, we're going to turn it on. And not surprisingly, this is our model number 2, ETS model number 2. So 0, 1, 2. So this is our AAM. All right, so then we can plot things, right? We can look at the in-sample plots. Do you see that this is doing a lot better job, right, compared to SES? Again, this is, or compared to AAN and ETS-AN. And now I want to show you the forecast. So these are the in-sample predictions. Let's look at the forecast. So this is where the difference between a method and model comes, right? Our method, our smoothing method, exponential smoothing method, did not create this confidence interval for us, but these models is able to provide that. So do you see that? And we set this coverage to 90%, so these are 90% confidence intervals. Okay, these shaded areas. So we have the point estimate. So for example, point estimate of the model is 462.204. This point estimate is exactly the same as our Holtz-Winter multiplicative, but now the difference is that it's going to give us this confidence interval. So these were, let me actually, if I can, yeah, these are in the test set predictions, right? We can also predict into the future with those confidence intervals. So this is how it looks like. And as you can see, even 48 months from the last observations, the confidence intervals are pretty decently narrow, right? So this is very good. This means that your data set is very well behaved and the model was able to create those confidence intervals relatively narrowly down into the future. For stock price, you're going to see that these confidence intervals are going to widen out a lot when we predict 48 months, for example, into the future. Okay, that's because of the nature of the data set. Now let's do another visualization. I want to compare the three models, right? ETS ANN, AAN, and AAM, multiplicative, and we can label them correctly. And so this is maybe the only downside of visualization using Pycaret. When we do multiple model, it doesn't show you the confidence intervals, even though we were able to create those confidence intervals and we created it for one model. But when you put multiple models, it doesn't show the confidence intervals for each model separately. So, or at least this is as far as I know. I tried to read the documentation, look at the source code. I couldn't figure it out, but if you could find it, how to do multiple models with confidence intervals at the same plot, just leave a comment. Thank you so much. All right, then we said that let's do this additive error and additive trend and multiplicative seasonality as our best model. We can look at the diagnosis plot for residuals. Again, we have seen something like this for the whole winter model. This is pretty much the same, right? So we talked about these things. Now we can get the parameters, right? So for example, we can say what were the parameters inside that ETS. This is what is inside that model. And finally, we can do a summary, right? So if we have trained a model, right? This is our winning model. I can look at the summary. So this basically helps you to write down the functional form, the estimated functional form of your ETS model, right? So it says, look at that. This is the model AAM. You can look at the log likelihood. Obviously, if you look at AIC, BIC, we're going to talk about these things later on. Actually, in the lecture video, in the theory lecture video, we talked about these things. What are they, right? But you cannot look at them in a standalone. You have to compare them with other ETS model, right? And the hope is that the best ETS model is going to give you the minimum value of AIC or BIC. Okay, but look at that. This is what I wanted to talk about is this. You can literally write down an equation for your ETS model. The smoothing level is this number, 0.37. It's significant. Your smoothing trend, the value for trend is this. Again, this is the reason that it's NaN. I'm not quite sure what it is, but probably this is a computation thing. The numbers were small, and then probably the variance, something divided by when it was calculating those t-stats, dividing by very small variance, it turned out to be a large number. So that's why we get these ones. There's the seasonality, that's the coefficient. And then these are the initial levels, right? L0, B0. So these are the ones that when I was talking about maximum likelihood estimation, we said the algorithm is going to start from some random numbers, and these are the optimal values. And then obviously we have 12, the seasonality periodicity was 12 monthly. Now we have 12 numbers for each of those values, right? So for example, if you're in December, and if you want to project into the future, next month is January, you look at the previous January. You don't look at previous month, which is December, right? You use the right number. Okay, so yeah, this is the model. We can go ahead and make some prediction with that model. So, but in order to make sure that, again, I'm gonna give you the benchmark model. Our benchmark model, we can call it naive. So from that experiment, I create this model, I call it naive, and then this is my benchmark. So these are the performance of the benchmark in the test set. And I can do seasonal naive. Seasonal naive is going to be a more fair benchmark because this data is seasonal, right? So then this is obviously, as you can see right off the bat, this is a better model because this is seasonal naive. So I would say if I want to think of a benchmark for this time series, at the very least, it should be S-naive. S-naive is not good enough itself because it doesn't include the trend. But I think in the theory lecture, we said that, as long as you have a fair benchmark, we call it. You don't need to make your benchmark unnecessarily complicated. So the point is that the benchmark for this data set is S-naive. It's not naive. So if your model can outperform these numbers, for example, the MAPE of 0.099, you have a good model. Okay. All right. So let's see, auto ETS. So we talked about it. Let's add all these models, right? So we have I'm combining everything we had so far in this notebook. I have naive model, I have seasonal naive model, I have SES method, Holt-Winter additive method, Holt-Winter multiplicative method, ETS ANN, ETS AAN, and ETS AAM. And finally, I add this one. If you leave something like this, it's going to do auto ETS for you, okay? So the auto ETS is going to go over 18 different combinations of the ETS model and give you the best one. Okay, so remember what were those 18 combinations? For the first error, we can have additive multiplicative, and then for trend, we can have 3, no trend, additive multiplicative. And then for seasonality, the same story, right? So that's why we do 2 multiply 3 multiply 3. So there are 18 combinations. So the auto ETS is going to use those 18 combinations and give you the best, right? So let's run this, compare the models, and see which one is the best. So the point is that the benchmark for this data set is S-naive. It's not naive. So if you want to think of a benchmark for this time series, at the very least, it should be S-naive. So number 7 is the best. So let's start from here. 0, 1, 2, 3, 4, 5, 6, 7. So the 7th one is ETS AAM. And the auto ETS also, which is number 8, is pretty much the same model. So the auto ETS is telling us that out of those 18 combinations you could have, the best one was this, the one that you kind of guessed it right away at the beginning by observing the data set. You said that, okay, this data set, it has an upward trend, so I need a trend. It has seasonality. The seasonality is increasing in magnitude. Let's do it multiplicative and additive error. So your first guess was pretty much close to the best you could get out of ETS. So hopefully this makes sense. And yeah, now we can do some predictions. This part is pretty much the same as what we did for the smoothing methods. We are going to do from that experiment, predict model, pass the name of a model. If I just do that, it's going to go ahead and give you the predictions in the holdout set. Holdout set is your test set, the last 12 observations. Okay, so let's go ahead and do that. That's it. So these are the predictions in the holdout set, right? And yeah, let me see if I can back out those numbers. So we're talking about these ones, right? So here, the first one. If you do AAM, the red one is 417.22. So that's for the AAM. Let's see if that number, hopefully that number is close enough, or should be the same, right? 417.225. Okay. All right. Then last step is to finalize the model. So this finalized model is going to go ahead and retrain the model. But now, instead of using the train set, it's going to use the entire thing, the train set and the holdout set. Basically, we call the test set. The 132 observations in the train set in this example, plus 12 observations in the test set, make it one train set, and then retrain the model. Now we know what is the best model, so we're going to retrain it one last time using the entire data set, and then call it finalizing the model, right? So let's go ahead and finalize the model. Now you have a model, this is your model, ETS, multiplicative, seasonality, period 12, and then trend additive. And now we can make predictions on unseen data. So you want to make prediction on something that we haven't seen before at all. So we are using the entire 144 observations, and you want to forecast into the future, right? So let me remind you the train test split. Remember, this was your train, the blue one, the orange one was test. The entire data goes all the way to December 1960. Now, I have a finalized model which is using this entire data set. The first prediction is going to be January 1961. Okay, so that's what we're going to do. So look at the forecast. Let's run it. I'm using the final model. This is what we have finalized on the entire data set. I'm forecasting 24 months into the future. And as you can see, the first starting number is January 1961. And these are pure forecasts into the future. I don't know if it is doing a good job or bad job because we're not saying test set and compare the predictions in the test set and actuals, right? There's no actuals here. There's no actual number for 1961 January. But these are the predictions with some confidence intervals as well. All right, so yeah, and of course you can see these numbers, right? So for example, let's look at the last one. December 1962, the number is 488.27, right? So if I do predict model on the final model, forecasting horizon 24, the last number should be the one that I just told you, 488.27. So this must be 488.27. All right, so that was pretty much it. So we trained the model, starting with the train set. We look at the performance in the test set. We pick the best model, combination of the features by looking at the performance of the model in the last 12 observations. Once we were happy with that model, we said, okay, I found the best model. Let's retrain it on the entire data set and use it for predicting into the future. So these are the steps that we do for every single model that we're going to cover in the next couple of modules before we go to the deep learning section of the course. All right. Once you're happy with that model, you're going to go ahead and save it from this experiment. Save model. This is your model you want to save. You can call it whatever. I call it best smoothing model. You save it, and when you save it, you're going to see something like this. where is it? Best smoothing model.pickle. No, this is it, the Python file that's going to save the model. And then later on, so this means that you don't need to retrain this model. Later on, you want to, let's say you have more information, you want to forecast into the future and things like that. You already have a trained model, you can simply load it, right? So I'm going to say my model that I'm going to work with, I'm going to load a model, and of course you have to point it to the right directory. As long as you're in the same directory and your model is in the same directory, you can simply call best smoothing model. That's it. If you're in the wrong directory, you have to specify what directory are you referencing to, right? So I can go ahead and load the model and then simply see what was the model that we created. So this is our auto ETS, multiplicative seasonality, and with additive trend and periodicity of 12. All right, that was pretty much it. We are going to repeat all these things a bunch of more times when we cover the ARIMA module, when we start working on the machine learning section of the course, and then hopefully by the time you have lots of chances to just give it a try and then explore all the functionalities of the Pycaret. This is a very powerful package for time series analysis, and I want you to just get familiar to that. Read the documentation of skate time, and it's pretty straightforward. Later on, I think by the end of the semester, if you get time, I will introduce you to one of the most recent time series packages, which is NixTLA, and then we can do more advanced time series analysis with that, including conformal predictions. All right, until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.